Good afternoon, dear students.
Good afternoon, ma'am.
Yes, good afternoon. Okay. Yes, so in our previous class, okay, so we have discussed the general properties, right, of transition metals. Then we had started with the preparation of compounds, right? Then we have seen the structures also. So I have told you to find the electronic configuration, that is the oxidation states, right? Did you find out? Yes, did you
Yes,
find out
ma'am.
the oxidation states of chromium? Yes, okay.
Ma'am.
So Na2CrO4. What is the oxidation state of chromium here?
6.
+6. Okay, fine. We'll see. Then Na2CrO4, then Na2Cr2O7
6.
+6. Okay. And K2Cr2O7.
8.
Fine. Okay, let us see. Let us see. Okay. So Na, I'll write it here. Na2Cr2Cr O4. Okay. Now sodium. So sodium is a alkali metal. Okay. And so it has a capacity to give 1 electron. So it commonly it will be in +1 state. Okay. And chromium we have to find out. So we'll keep it as X. And each oxygen is what? Each oxygen is -2. So let us substitute. So there are, yes, so there are 2 sodiums. So we'll write 2 into 1 plus X plus 4 into -2 equal to 0. So 2 plus X minus 8 equals to 0. So X -6 is equals to 0. So X is equals to +6. Correct. So first one is correct. +6 is correct. Now we will do Na2Cr2O7. Okay, Na2Cr2O7. So Na2, so let me take another. So Na2Cr2O7. Now here again sodium +1. So 2 sodium. So +1 plus. How many chromiums are there? 2. So we'll keep it as 2x plus 2 equals to 0. So 2 plus 2x minus 7 to the 14 equals to 0. Then 2x minus 12 equals to 0. X 2x is equals to 12. X is equals to 12 by 2. So x is equals to 6. So this is also correct. Now let's see for the next K2Cr2O7. Okay. So each potassium is +1. So +1 into 2 plus 2x plus 7 into -2 equals to 0. So 2 plus 2x minus 14 equals to 0. 2x minus 12 equals to 0. Then 2x equals to 12. So x is equals to 6. So here also it is 2x. Potassium here is 7, 12, 14. Okay, then this 2, 12. Yes. So it is +6. So here, everywhere the state is same. Okay, it is +6 itself. So we have seen in KMNO4, okay, we have seen the change in oxidation state of different. Okay. Now here we had to see the structures, right? We had to see the structure of So let us see. So last class we have seen the properties. So we have left with the structure. So I'll draw the structures of magnet ion and permanganate ion. So manganate ion, manganate ion magnet ion, this is Mn O minus, double bond O, double bond O, and single bond like this. Okay. So this is a tetrahedral structure. So very important. So please note down the structures of magnet ion. So the magnet ion and permanganate ion. Okay, both the structures are tetrahedral in shape. So this is a magnet ion, permanganate. So magnet, permanganate will be Mn. So double bond O, double bond O, double bond O, and single bond. Okay, and this is which color? Magnet ion is green color, and this is purple in color. Okay, so the Mn, that is MnO4 2 minus. Okay, so this is MnO4 2 minus. This is paramagnetic ion because it consists of one unpaired electron. Okay, it consists of one unpaired electron. But for magnet ion, that is MnO4 minus, it is diamagnetic in nature. Okay, because the pi bonding takes place by overlap of p orbitals of oxygen with the d orbitals of Mn. So permanganate is a diamagnetic in nature, and magnet ion uh, paramagnetic in nature because there is a presence of one unpaired electron. Okay, so let us go. So today we are going to start with the F block element. Okay, so we have completed the D block element. So we are going to start with the F block element. So F block elements, they are called as what? They are called as the inner transition elements. What they are termed as? They are termed as the inner transition elements. Okay. So in this elements, what will happen? Okay, the f orbitals of the ultimate shell is gradually filled with electrons. Okay, and their general electronic configuration is what? It is n minus 2. So let me write the general electronic configuration. N minus 2 F 1 to 14, n minus 1 D 0 to 1, NS 1 to 2. Okay, so this is the general electronic configuration of F block elements. Okay, it is of F block elements. So this is general electronic configuration of F block elements. So this F block elements, it consists of two series. Okay, it consists of two series. One is the lanthanoid series and another is the actinoids series. Okay, now this lanthanoid series, these are known as the rare earth metals. What they are called as? They are called as the rare earth metals. Okay, and what are actinoids called as? Actinoids are called as the radioactive elements. What they are called as? They are called as the radioactive elements, that is from thorium to lawrencium. Okay, that is Lr. So up to there, it is called as what? They are the radioactive elements. So radioactive elements mean these are the man-made elements. Okay, now so first we are going to start with what? We are going to start with the lanthanoids. Okay, let us start with the lanthanoids. So as we know, so in lanthanoids, there are 14 elements, and in actinoids, there are 14 elements. Okay. Now lanthanoids. So which are the elements present in lanthanoids? Okay. So which are the elements? So the lanthanoids. So let us study about the lanthanoids. Okay. So the lanthanoids, the elements, they start from lanthanum. Okay, I'll write the symbol. Okay, again, so lanthanum is the first element with the atomic number 57. Then you have cerium. Okay, you have cerium with the atomic number 58. Then you have praseodymium. Okay, that is, it is represented by Pr. The atomic number is 59. Then you have neodymium. Okay, neodymium, it is represented by Nd. It is 60. Then you have promethium. Okay, promethium, it is 61. Then samarium. Okay, samarium, Sm, it is 62. Then is europium, that is Eu, 63. Then you have gadolinium. Okay, that is Gd. gadolinium, GD. Then you have terbium, okay, terbium, TB, it is 65. Then you have dysprosium, okay, you have dysprosium, that is 66. Then you have holmium, okay, you have holmium, HO with 67. Then you have uh, erbium, okay, erbium, that is ERBIUM with 68. Then you have thulium, okay, thulium, that is TM, okay, it is represented by thulium is TM, 69 with atomic number. Then you have terbium, okay, terbium, that is EPI, YP, that is 70, and the last is lutetium, okay, lutetium, that is LU with 71. So these are the lanthanide series. It starts with your lanthanum and it ends with your lutetium, okay. The general electronic configuration, as we know, okay. Now for lanthanoids, the lanthanoids you fill up to how? Just I'll show you. So the general electronic configuration of lanthanum, here it is C, that is xenon 4F 1214 5D01, okay, 6S2. Fine. So this is the general electronic configuration of what? Your lanthanide series, okay, of your lanthanoid series. So please note the general electronic configuration of lanthanide series. It starts from 57 and it ends up to 71. Okay. Next, what is the, so this is very important. So mark this as important for 1 mark, the general electronic configuration. Okay. So it is xenon 4F 1214, 5D021 and 6S2. Then next is the atomic size. Next is the next property of lanthanoid is atomic size. Okay, so the atomic and ionic radii of lanthanoids, it will gradually decrease. What will happen? It will gradually decrease. Okay, that is from lanthanum to your lutetium. From lanthanum to lutetium, the size is going on decreasing. Okay, why? What is the reason? This decrease, okay, this decrease in the size, gradual decrease in the size, it is due to called as lanthanoid contraction. It is due to what? Lanthanoid contraction. So it is due to what? It is due to lanthanide contraction. So the atomic and the ionic radii of lanthanoids, they gradually decrease, okay, from lanthanum to lutetium with the increase in the charge. As the charge increases, the size go on decreasing. So this is due to what? It is due to lanthanide contraction. Okay, now what is this lanthanide contraction? So this lanthanide contraction, it is due to the poor shielding of 4F electrons by other. Okay, that is in the second inertial. So in the second inertial, you can see that there is a poor shielding of 4F electron. So because of the shielding of 4F electron, the size goes on decreasing from lanthanum to lutetium. So very important property, why the atomic size of lanthanoids decreases. So the reason is it decreases, okay, as you move from left to right. That is due to the increase in nuclear charge, and the reason is due to lanthanide contraction. Lanthanide contraction means poor shielding of 4F electron. So what are the consequences? Okay, what are the consequences of lanthanide contraction? Okay, so the elements of 5D series. So when you see the elements of 5D series, they have almost similar radii as compared to 4D elements. And the 5D series elements, the atomic radii is similar. The atomic radii is what? Atomic radii is exactly similar. Okay, it is exactly similar. So the atomic radii in 5D and 4D series, they are exactly similar. Okay, so that is the reason zirconium is having 160 picometer and hafnium is having 159 picometer. So this is the atomic radii which is absorbed observed in the elements of 5D and 4D series. So this is the reason, okay, because of poor shielding, because of the intervention of 4F electrons, okay, what happens? We can observe the lanthanide contraction. So because of that, the elements present in the 5D and 4D, they are having almost similar size. Okay, so this can be a question. Mark this as important. I have told you in the previous class also. That is why zirconium and hafnium are having similar size. Okay, so they have same size, almost similar size, because due to lanthanide contraction, that is intervention of the 4F electrons. Okay, because of poor shielding of 4F electron. Okay, then second, consequences. So consequences are also important. So there can be a question: explain lanthanide contraction and give the consequences of lanthanide contraction. So like this, the question can be asked for 3 marks. So explain lanthanide contraction with its and write its consequences. Okay, so mark this also question as important. So the second consequences is what? Due to lanthanide contractions, the elements of 5D and 4D series, they occur together. Okay, they occur together in nature and they are very difficult to separate. They are very difficult to separate. Okay, so this is the reason why the elements which are present in 5D and 4D series, they occur together. So because of lanthanide contractions, the elements which are present in 5D and 4D series, okay, they uh, they are very difficult to separate. Okay, so this is the two consequences. So these are the two general properties which we have discussed. Next is the states. Okay, next is the oxidation state. So the common oxidation state seen by lanthanoids is what? The common oxidation state seen in lanthanides is +2. Commonly it is +3. So +3 is the most common oxidation state which is shown by the lanthanoids. Okay, but however, the different oxidations shown by the elements are +2, +4. Okay, so +2 and +4 are also shown by the metal ions in the solution form or in the solid form. Okay, so the most common oxidation state of lanthanide is +3, and commonly +2 and +4 also is seen. Okay. Now this irregularity. Now this irregularity, it is due to the extra stability of half or completely filled F subshell. That is, for example, the oxidation state, okay, of cerium is +4. The oxidation state of the cerium is +4. It is due to the noble gas configuration. Okay, but it is strong oxidant. Strong oxidants means what? It has the ability, okay, to oxidize other. It has the ability to oxidize other and itself undergoes reduction. So oxidizing it, and it undergoes reduction. Okay, so Ce+4, it oxidizes other and itself undergoes reduction. Okay, so this is the about oxidation state. So remember, in oxidation state, so most common oxidation shown by the lanthanide is +3, +2 and +4 oxidation states are also exhibited by lanthanoids. Next, so let us see some of the physical properties. So these lanthanoids, they are silvery white soft metals. Okay, they tarnish rapidly in air. So they get tarnished rapidly in the air. Okay, they melt at high temperature. So these F block elements, they melt at high temperature, and they are good conductor of heat and electricity. Okay, they are good conductor of heat and electricity. And what happens? Hardness. Okay, about hardness, when we talk about hardness, so as the atomic number increases, okay, as the atomic number increases, the hardness also increases. So they go, so as you proceed from lanthanum to lutetium, as the atomic number is increasing, what is happening to the hardness of the metal? It is becoming more and more hard. Okay, it is becoming more and more hard. So hardness also increases. Okay. Next, formation of colored ions. Okay, so what is the about colored ions? So these are the so next is colored ions. Okay, so the as you know that lanthanoid series, they occur in the +3 state. Okay, so most of the lanthanoid series, they are trivalent in nature. So trivalent lanthanoids, they are colored. Okay, they are colored in solid state as well as in the aqueous state. So why the color property is seen, students? Why the color property is shown by the transition elements and the inner transition element? It is due to the presence of unpaired electrons, right? Due to the presence of unpaired electrons, the color property is shown by the different ions. So many trivalent lanthanoid ions are colored. So in solid state as well as in the aqueous state. Why? What is the reason? It is due to the presence of unpaired 4f electrons. Okay, unpaired f electrons. Understood? So La plus 3 and Lu plus 3. Okay, so these are only colorless. So these are the two exceptionals where these are colorless, while the rest other lanthanoids are colored in nature, because lanthanum plus 4 F electrons are 0 and lutetium plus 3 F electrons are completely filled. So these are colorless. We have seen in the transition metals also. Whenever you have a D0 system or D10 system, the electrons are they are what, colorless compounds, right? They are colorless. These lanthanoids are these lanthanoids are very reactive metals like the alkaline earth metals. Okay, so these are general properties. Now, how are the different reactions taking place in lanthanoids? So we'll see the various reactions. Okay, we'll see the various reaction with lanthanoids. So what are the chemical properties? Okay, what are the chemical properties means what? How it will react. Okay, how it reacts with the so lanthanum, okay, metal lanthanum, when it reacts with oxygen, okay, when it is reacting with oxygen, when it burns with oxygen, what it forms? It forms oxides. Okay, it forms oxides. So any lanthanide metal, okay, take it as M. When it reacts with oxygen, what it forms? It forms, okay, it forms oxide. So when it burns in oxygen, it gives oxide. When it reacts with nitrogen, okay, when it reacts with nitrogen, it forms what? Nitrides. Okay, it forms nitrides. Then when it reacts with sulfur, it forms sulfides. Okay, it forms sulfides. Okay, then when it reacts with carbon, it forms carbides, metal carbides. Okay, it forms metal carbides. So these are the different reaction. When lanthanides, when it reacts with the halogen, okay, it forms metal halides. What it forms? It forms metal halides. Okay, so these are the different reaction. Then when it reacts with water, okay, it forms hydroxide. What it forms? Metal hydroxide. So these are the different reactions of lanthanoids, that is your lanthanoids. Okay, so how it reacts? So if it reacts with oxygen, it forms oxides. So this is the formula. You can take any metal of lanthanide. Okay, it forms respective oxide. It forms the respective oxide. And with nitrogen, it will form nitrides. Okay, metal nitrides. Then with sulfur, it gives you sulfides. And with the carbides, okay, with carbon it forms metal carbide. And okay, so these are the different reactions, okay, which is we can see with the lanthanoid. Is it clear? Okay, so these are the chemical properties. What do you mean by chemical properties? Chemical properties means how it reacts, okay, how it reacts. So how it reacts with oxygen, what product we'll get when it reacts with nitrogen, sulfur, carbon, okay. So these are the different products which is obtained. Next is the mish metals. They contain lanthanoids about 90 to 95%. Okay, it consists of what? Cerium. Cerium consists of 40 to 45%, and lanthanides and neodymium as 44%, iron 4.5%, calcium, carbon, and silicon used in cigarette and gas lighters, toys, tank, and tracer bullets. Okay. So what are these mish metals? Very important. So please make a note of this. What is mish metal? Mish metal means nothing but like alloys. Okay. We know what are alloys. Alloys are nothing but when metals and non-metals combined, when two or more metals or non-metals combined, they give you alloys. So similarly, mish metals. Okay, mish metals is also mish metal means what? It is made up of the lanthanide metals. Okay, it is made up of lanthanide metals. So it consists of 90 to 95% of the lanthanide metals, and remaining will be the traces of calcium, carbon, and silicon. So these are the importance. So please make this important. What are mish metals? Okay, mish metals means it is made up of it contains maximum of lanthanoids, that is 90 to 95% of lanthanides, iron about that is iron about 4 to 5%, then some traces of calcium, carbon, and silicon. Okay, so these are the this is the what about mish metals, very important. Now where these mish metals are used, it is used in cigarette, it is used in gas lighters, okay, toys, tanks, and tracer bullets. Okay, so these are the okay, so what are the other uses of lanthanoids? Okay, what are the uses of lanthanoids? Let us see what are the uses. So, as we know, so first uses, it is used in the production of alloys. Okay, alloy steel. That is your example, your mish metal. So, there can be a question, what are mish metals? So, mish metal means what? Okay, it contains lanthanoids, that is about 90 to 95%, then iron about 4.5%, and traces of sulfur, carbon, calcium, and aluminium. So like this you have to write. Okay. And they are also used where mish metals, it is used in the bullets. Okay, to make the bullets, then bullet shell. Okay, bullet shell and lighter. Okay, lighters. So that then the mixed oxide, whatever the mixed oxide of lanthanides are there, okay, they are used as a catalyst. They are used as a catalyst in petroleum. Okay, in petroleum crackering. In petroleum crackering. Okay, then some of the lanthanide oxides are used as phosphors. Okay, they are used as phosphors in TV screens and Okay, so these are some of the uses, and they are used in screens and fluorescing surfaces. Okay, so these are the uses of your lanthanides. These are the uses of lanthanides. Okay, so is it clear? Is it clear up to here?
Yes, ma'am.
Okay, so this is about this much is importance. Okay, these are the important things about lanthanides. So the important questions from here, as I've told you. Okay, so there can be a question on base this general electronic configuration of F block elements. Okay, then general electronic configuration of lanthanoids. Then what are mish metals? What are niche metals? Then about lanthanoid contraction, explain lanthanoid contraction and write its consequences. Then about atomic size. Okay, why hafnium and zirconium are having similar size? So like that, the questions are asked there. Okay. Then about oxidation state. So these are the important things about lanthanides you need to know. So next we are going to start with the actinoids. Okay, let us see about actinoids now. Okay, so next is about actinoids. So let me make this blank. Okay, so actinoids, next series in F block, the actinoids. Okay, now here, which are the elements? It starts from actinium. It starts from actinium with atomic number 89. Then thorium with atomic number with 90. Okay, atomic number 90. Then proactium with atomic number 91. Then you have uranium, okay, with 92. Then you have neptunium, okay, you have neptunium 93. Then you have plutonium, okay, plutonium with 94. Then you have americium, okay, you have americium, that is Am, with 95. Then you have curium, Cm, okay, not Cu, Cm with 96. Then you have berkanium, okay, that is Bk 97. Then you have californium, okay, californium Cf 98. Then you have einsteinium, that is, so these are some of the man-made uh, elements, okay. So they are named after that scientist. So the names are like this, okay. Then this is 80, 99, einsteinium. Then you have fermium, Fm 100. Then you have mendelevium, that is Md 101. Then you have nobelium, Nb, No, okay, No with 102. Then lawrencium, Lr 103. Okay, so these are the, it starts with Rm, okay, that is radon 61 7s2. Okay, and then radon 6d2 7s2. Then radon 5f2 6d1 7s2. Then uranium is what? Radon 2. Neptunium, radon 5f4 6d1 7s2. Then radon 5f6 7s2. Then americium, radon 5f7 s2. Then curium, radon 5f7 6d1 7s2. Okay, then pi f9 2. So, okay, you can see here the electrons are entering into the F shells, okay, in the F shell.
So, ma'am, 96 pi F8 alva, ma'am.
96
pi F8.
here 96. Just a second. Radon, then 9f7. So if I write the filling of electrons, so here it will be 7. Then the electron is going to 60. Okay, let us see. Okay, first I'll write others, then I'll see later. 99, 2, then radon, 100, pi F12, 7s2, radon, pi F14, 7s2, radon, pi F11, 12. This is 13, sorry, this is 13, this is 14, 7s2, then nobelium, pi 14, 7s2, then radon is pi F14, 61, 7s2. Okay. Okay, now radon. Okay, so when we see the actinoid series, okay, now actinoids, what you can write the general electronic configuration? Yes, actinoids. Can you tell me actinides general electronic configuration? It will be radon. Okay, then 5F 1 to 14, 6D 0 to 2, sorry, 0 to 1, and 7s2. Important, mark this as important. The electronic configuration of actinoids is what? Radon. Okay, radon 5F 1 to 14, 6D 0 to 1, and 7s2. Okay, so this is the general electronic configuration. Now, when we are talking about your M, okay, now here what is happening here? It is so when the filling of electron is taking place, okay, so after this we are filling it into 60. Okay, so ambrosium, so it is correct. So radon, okay, it is radon. Then you get what? 96, no, so 5 pi f7 61 7s2. So when the filling of electron takes place, so we are entering the electron into the 61, so the electron will accommodate in 61 here. Okay, so this is correct. So here 7, because it is half filled, so we are not disturbing the see, when you write the 14 electrons, right, so there will be 7, 1 2 3 4 5 6 and 7. So 1, 2, 3, 4, 5, 6, 7. So if you put that one electron, so it will prefer to be in its half filled, okay, half filled stage. So it is 5f7. Then the next electron is going into 61 because already s orbitals are filled. Okay, 2 electrons. So it will go, the next electron will accommodate into the 61. Okay, so this is the reason. Then here what happens? So because it now 97, okay, now 97, it has to be filled here. So what is happening? So after 7 electrons are filled, then the next electrons are filled here only, and okay, and the remaining into 7s2. So like this here, again d electrons are not coming into picture here, because 5f7, whenever it is in 5f7 form, it is half filled. Half filled means it is stable. Okay, it is stable. So these are the electronic configurations of your actinoid series. Okay, these are the general electronic configuration of actinoid series. So please remember this general electronic configuration, very important for 1 mark. That is radon. I'll write it here: 5F1 to 14, 6D0 to 1, and 7S2. Okay, so for your actinoids, Okay, for actinoids. Good. So next we'll see the ionic size. So let us go back to our PPT. Okay. So actinoids 89 to 103. Okay, the names of the series comes from actinium, the element that marks the beginning of the series. So why it is termed as actinides? Because the first elements from the series is actinium. So it is called as actinides. Okay, and all the members of this series, they are having similar properties. They are all having similar chemical properties. Okay, then we will see the ionic size. What will happen to the ionic size of the actinoids? So here also there will you can observe a gradual decrease. You will observe gradual decrease in atomic and ionic size. What you can observe? You can observe a gradual decrease in atomic and ionic size of actinoids. Okay, what is the reason? What is the reason? It is due to poor shielding of 5f electrons. Okay, it is due to what? It is due to poor shielding. It is due to poor shielding of 5f electrons by other. Okay, so this is a reason for what contraction. What type of contraction is seen? It is actinoid contraction. So what type of contraction is observed? It is observed a actinoid contraction. So this contraction, when you are comparing this contraction with the lanthanoid contraction, this contraction is greater. Okay, in actinoid contraction, the actinoid contraction is greater as compared from the elements of lanthanoid. So in the actinoid contraction, okay, you can see in ionic and atomic and ionic size, it gradually decreases. Okay, why it decreases? Because of presence of the 5f electrons. Because the electrons, okay, because of the poor shielding of 5f electrons by the other, okay, you can observe the actinoid contraction compared to lanthanoid contraction. Okay, next, oxidation state. Next property is oxidation state. Oxidation state. So as you know, lanthanoids, they will show +3 commonly, and +2 and +4 are exhibited most. Okay, in actinoids, they will show variable oxidation state. So they will show variable oxidation state because there is very small energy gap between the 5f electrons, 60 electrons, and the 7s energy. Okay, so the energy between the 5f, 60, and 7s is very small. So the energy gap is very small. Hence, all the electrons are used for bonding. So hence all the electrons are used for bonding. Okay, hence all the electrons from these orbitals, they are used for the bonding. And generally here also the oxidation state shown by the actinides is +3. Okay, and what will happen? The oxidation state, okay, it increases as you go from top to bottom. So from +7, +4 to +6 and +7. And the maximum oxidation state. So which do you know which is the element which will show the maximum oxidation state? Yes. So the maximum oxidation state which is shown by the element. So it is a Neptunium. Okay, Neptunium is the element. So please remember. So from CET point of view, also it is very important. So Neptunium is the element. Okay, that is represented by NP. So it is the element. Okay, which shows the highest oxidation state of +8. So +8 is the oxidation state shown by Neptunium. Okay. So actinoids. So as so these are the oxidation about the oxidation state. Then when we talk about the physical properties, these are highly reactive. Okay, the actinoids, they are highly reactive and they are silvery white. Okay, they are silvery white and they appear silvery white. Okay, so these are the properties of actinoids. Okay, so binding energies of 5 electrons lower. So due to the lower binding energies, they show variable oxidation states like +4, +5, and +6. Uranium exhibits +6 oxidation state. Okay, in this too, it is due to lanthan actinoid contraction. Okay, then also most of the ions are colored by uranium. So uranium +3 is having red color, while uranium +4 is having the green color. Then they have the actinoids, they have a greater tendency to form complexes. Okay, as you know, actinoids, they are radioactive elements. Okay, most of the elements are radioactive because they are man-made. Then the compounds of the actinoids, they are basic in nature and they form oxocation. Okay, oxocat ions. So these are some of the properties. So general configuration, you can see your general configuration. Then oxidation state, most commonly it will so because of the less energy gap between the different orbitals of 5, 60 and 7s, the general oxidation state is +3 and they are very reactive. And actinoids, they react with oxygen, halogen, hydrogen and sulfur like lanthanoids. So we have seen the various reactions in lanthanoids, right? The same way actinoids also react with the different elements like oxygen, halogen, hydrogen and sulfur. Okay, and they form corresponding oxides, halides, okay, hydrides and sulfides. Then actinoids, they are radioactive in nature. Why? Because of this, it is very difficult to study their chemical nature. Because they are very radioactive in nature, it is very difficult to study their chemical properties. Okay. So now the difference between the, okay, before this, so difference we will see in the next class. Okay, so it will be again taking more time. So let me sum up. Okay, we'll take some of the important, you can write down the questions. So the question can be from this part is what is actinoid contraction? Okay, then so as I have told you in actinoid series, which is the element which shows a higher oxidation state, it is neptunium with +8 oxidation state. Then in give reason type of question, so what are the different questions? Give reason. Actinoid shows variable oxidation state. What is the reason why actinoid shows? Because of less energy between the less energy gap between the 5, 60 and 7s orbitals. Okay, or almost identical radii. What is the reason why they have same or identical radii? It is due to the lanthanide contraction. Then next question. What is lanthanide contraction? Write any one consequences of it. Okay, you have we have studied 2 consequences, so you have to study both the consequences. Either they will ask 2 consequences or any one, so depending upon the marks. Then the next question, what is the formula of the product formed when lanthanoid reacts with, so if lanthanoid reacts with halogen, what it forms? Yes, what it forms? Yes, when lanthanoid reacts with uh, halogen, what it forms, students? It will form halides, right? It will form halides. We have seen just now. Here, right? It will form halides. Respective halide is formed when lanthanide reacts with metal, halogen. Then when it reacts with nitrogen, it forms nitrides. When it reacts with sulfur, it forms
Sulfide.
sulfides. Okay. Then, so next question, give reasons. Cerium shows +4 oxidation state. Cerium shows +4 oxidation state. Okay. One question, find out the answer in the next class. I want the answer from you all. Then one more question. Actinoid contraction is greater from element to element than lanthanide contraction. So take these two questions and find out the answers for this. Okay. So I'll be asking the answers for this in the next class. Is it clear? Yes. So these are the important questions from your lanthanoids and actinoids. Okay.
Ma'am,
I
can you
hope-
repeat second question?
Yes. Just a second. Actinoid contraction is greater from element to element. Actinoid contraction is greater from element to element than lanthanoid contraction. Means what? Actinoid contraction is greater, okay, as compared to the lanthanoid contraction. What is the reason? Then cerium shows +4 oxidation state. Cerium shows +4 oxidation state. So in the next class, I'll give you some more questions, okay, from this particular chapter, so that it will be very easy for you also to prepare. Okay, fine. So any doubts? So these were some of the important things. So we are left with a very small part in the next class. Okay. Then with that, I'll give you some questions also, so that it will be very helpful for you. Okay, fine. So any doubts? Okay. Others, any doubts you have? Fine. Okay. So I'll end the session here. Okay. We'll meet in the tomorrow's class. Thank you.